Hey guys, how's it going? It's Monster and coding time. So, I'm finally on my spring break and have time to record the video. And first of all, I'd like to say that one of my really good friends that I've been doing coding interview prep for a while got to one of the final stages to be a software engineer at Microsoft. So, big congrats and good luck to David. And today we're going to be solving one of the most asked dynamic programming questions by Two Sigma, Microsoft, and Facebook. So let's hop on it, guys. So the problem we're going to be solving today is best time to buy and sell stock 3. Actually, we're going to be solving two problems today. It's this one and best time to buy and sell stock 4, which the problems are pretty much the same and the solution is really similar. So I thought we might as well. Don't really freak out that it's a hard question. It might be quite hard to understand at first, but I think that it actually really tests how well you understand dynamic programming. And even though I'm not really good with the dynamic programming questions, I was able to solve this. So let's actually read what they want from us. Say you have an array for which the ith element is the price of a given stock on a day I. Design an algorithm to find the maximum profit. You may complete at most 2 transactions. You might not engage in multiple transactions at the same time. For example, you must sell the stock before you buy again. Let's look at the examples. So the first example is we've got this array of numbers. The output should be 6, and the explanation is that you buy stock on day 4, which the price is 0. Day 4, I guess, is this one. And sell on day 6, which the price was 3. Profit is obviously 3, then buy on day 7 with the price 1 and sell on day 8, price 4, and the total profit is 3. Buy on example number 2, buy on day 1, price 1, and sell on day 5, price 5, profit 4. You cannot buy on day 1 and buy on day 2 and sell them later, as we cannot engage in multiple transactions at the same time. So in this example, we're going to use only one transaction. Example 3 is the sequence is decreasing, so we cannot get any profit out of buying stocks here, so we don't use any transactions, and max profit is equals 0. So let's actually start looking at the ways we can solve this problem. So let's start looking at our problem. We have our original example number 1, the array 335000314. Essentially, what you want to start thinking about is how you would solve this problem if you had just one transaction. Obviously, you would probably just find the minimum number so far, maximum number so far, and then you would just subtract one from the other and get the maximum profit, right? Okay, so how would we utilize this information to get the maximum profit out of 2 transactions? We'd probably start at each given point of time, which is each price is a separate day. We can calculate the profit so far with one transaction till day 3, for example, and then split the problem and try to calculate the maximum profit for the other part of the problem. So we would think about some divide and conquer algorithm, which we can split the problem, find, for example, the solution for this part, find the solution for this part, and combine them and see if it's the most optimal overall solution. So I suggest we have a table for our dynamic programming solution, which each row in the table is going to be k, which is going to mean the transaction, how many transactions were processed so far. So we would start with 0 transactions, which at 0 transactions, we obviously don't have any profit at any given moment of time just because we don't buy and don't sell stocks. Okay, then we obviously have 1 transaction. So how would we do that? We would at each given point of time calculate the maximum profit. For example, this point of time we have 0 just because at first day we cannot buy and sell. Even if we buy and sell, we're gonna get 0 profit. Second day it's 3 minus 3, 0 profit. Third day we have 5 and our minimum here is 3, so we can subtract 3 from 5 and get 2 maximum profit. Day 4 maximum profit is still going to be 2 just because 0 is less than 5 and 3. Day 4 still 2. Day 6 is going to be maximum profit is going to be 3 just because we have a day 5 0, day 4 0. We can buy stock at 0 and sell it at 3, so maximum profit 3. Day 7 maximum profit is still 3. Day 8 maximum profit is going to be 4 just because we can buy stock at 0 and sell it at 4. Okay, that was the easy part. Obviously, just simplified problem, just 1 transaction, easy. Let's start looking at 2 transactions. Start with 0, obviously. Second, 0, just even with 2 transactions, we cannot get any more profit. Day 3, still 2, doesn't matter how many transactions we got, cannot get any more profit. Day 4, same profit. Day 5, same profit. Day 6 is where it gets interesting because the profit would be 5, because we would be able to buy stock at 3, sell it at 5, then buy it at 0 and sell it at 3. So the total profit would be 5. That's the maximum profit at this point of time on this day. Day 7, still 5, no way to get any more profit. And day 8 is our overall answer, which is supposed to be 6. So essentially there are 2 solutions, might be 2 solutions, which is we buy at 3, sell it, buy at 0, sell at 3, buy at 1, sell at 4, which gives us 6. Or we buy at 3, sell at 5, buy at 0, and sell at 4, which is also going to give us 6. Overall answer. So let's look closer into our table. We got the table, we figured it out. Now we need to find some pattern in the table so we can actually construct the dynamic programming formula for our solution. So let's see how we get 5 here. So how we get 5 here, we'll look at the previous transactions before this specific day, before day number 6, and we see where we get the maximum profit. We had the maximum profit, it was day 5, day 4, day 3. Essentially we bought the stock at 3, sold it at 5. Okay, we figured it out, we just look at the previous transaction. That's one step. Then what we do after getting this previous transaction and figuring out where the max was for this transaction, we get the next value where we sold our transaction where it was the last maximum, and figure out where we can sell it at this. For example, this current date, we buy it at 0, sell it at 3. This is how we get 5. So essentially, we would have 2 steps. That's why we get the maximum out of 2 steps. We have 2 possible ways of developing the situation. We either every single point of time we either buy and sell the stock, or we just do nothing, meaning that we get that previous value that was the maximum. So the first part of the dynamic programming formula is the maximum profit that we had at the previous day at the same amount of transactions, meaning here, like at 5, we would look at 2. We would get 2. And the second part would be how many. The second part would be we would get 3 here. We would get some value where we would buy the stock, which is gonna symbolize prices J, which is, we have prices I, which is 3, prices J, which is 0, and we'll look at our previous dynamic programming solution, which is 1 transaction less, and the day before we buy our stock, meaning this is the day we bought our stock, this is the day we sell our stock, and this is the maximum profit that we could get before buying our second stock, before completing our second transaction. So this is going to be our dynamic programming formula, and the next step would be efficiently implementing it. So let's try doing that. Let's just to remember our dynamic programming formula, we write it down here. I equal max of dp same transaction day before, and prices I minus prices J minus prices J, and we would add dynamic programming the solution we stored for last transactions and day before buying the transaction, which is prices J. Okay, so first thing we want to do, we want to create our dynamic programming table, which in Python there's actually a really nice way to do that. It's for I in range. And so prices, and for I in range range 3, just because we need to include the step for where the transactions are going to be 0. Okay, we have that. What's our next step? Our next step would be to iterate over all of the transactions, which is going to be for k in range. We skip the transaction 0 just because we're not going to update anything there, and to 3. I Then what we want to do is to have a variable for maximum, something like max so far, which is going to be infinitely small, negative infinity. Then we're iterating over each day for I in range still from 1, just because on day 1 we cannot really get any profit, so we just skip it. Length of prices. What we're trying to do here, we're trying to update max so far with our previous max so far. So at each point of time, we know essentially at each max so far would symbolize this part, which is profit we could have before this day, and the price of selling our stock. So we know which is the maximum number for that, so we can calculate our general dynamic programming formula. So how we would do that, it's dpk minus 1 I minus 1, and we would subtract prices I minus 1. We would subtract prices I minus 1. So we figured out our max so far, and we figure out our max so far. Now we're trying to update our dynamic programming table, which is gonna be dpki max of dp according to our formula ki minus 1, and here we would have prices I plus max so far, right? And that would give us our actual formula. I think it's correct. And at the end, we would return dp last value of our dynamic programming table. Let's run it and see. Yeah, so it gives us the correct result. Let's actually run the whole code and see if last index out of range.
2,000 years later.
Okay, yeah, sorry, it was my bad. Before actually filling up the dynamic programming table and checking for the solutions, we need to make sure that prices is actually existing, so wouldn't have the empty input. Okay, so yes, our solution is correct. It works. Is there a way to do better? So right now we can analyze the complexity which is time complexity is going to be big O of kn, which is, we can kind of say that k is constant, so it's big O of n, but let's keep k here. It's for our next problem. Space complexity is also big O of kn, because we're filling out the whole table, and the whole table needs k multiplied by n space. So how can we improve our solution? If you look closely enough, essentially we're not using the whole table when we're calculating each next step, each next transaction. So at each transaction, we just using the part of the table where we have k minus 1, which is just one last transaction, and I minus 1. So one of the ways to improve our solution, we could improve our space complexity for this specific solution. We would store zeros here, and we would also have max so far array, which would also store 0 for I in range 3. We would switch a little bit our loops for k in range 1, 2, 3. We would have max so far k, max so far k. Wait a second. Max so far k. Here we would get rid of k minus 1, which would be prices I, if I'm not mistaken. Here we could get rid of dp, I minus 1, dp, and we would keep prices k, and we would just return the last value of dp. So essentially what we're doing, we're calculating max so far for each of our steps, each of our transactions, and instead of calculating all of the, so essentially at the first solution we were calculating max profit for all of the days at one transaction and then all of the days at the second transaction. Here we're going kind of in an opposite way. We're calculating the we're calculating max profit for first day for 0, 1, 2 transactions. Then we're calculating the max profit for the second day for 0, 1, and 2 transactions. And this way we're saving so much more space. I think wait a second, I'll check my solution.
You dumb bastard.
Okay, so essentially, sorry about that. We want to obviously initialize this value to smallest value possible, and here we want to start from 0, not from 1, just because in cases like this one, we want to be able to calculate max so far also for the first value, meaning that we might buy the stock on the first day. Let's try running the code. Okay, so gives us the accepted output. Let's try submitting it. Okay, it also gives us the accepted successful output. So in this case, we optimized our solution to be just space big O of n, and essentially keep in mind this solution. I'm gonna copy it. Is there a way to do even better? Yes, there is, and I'm gonna leave it for you guys as a homework. I'm gonna also attach all of the code in the link to this video under this video and description. So go and check it out if you're still having troubles to actually implement the even better version. Essentially, as you see here, our arrays are really small. So this array is only 3 values, which the first dynamic programming with 0 transactions is going to be 0, so we can completely ignore it. We can switch this solution just to keeping 4 static, just 4 regular variables. Here, max so far, the first max is also going to be 0, so you can ignore it. Essentially, you can get rid of this k by switching to just regular variables, having 4 variables. One is going to be sell 1 for the first, buy 1 for the first transaction, sell 1 for the first transaction, buy 2 for the second transaction, and sell 2 for the second transaction. And using those variables, you can implement this dynamic programming formula. I encourage you guys to go ahead and try it out at home. And if you have any troubles, you can reach out to me and I'm gonna help you out and explain the solution. So, as I promised, we solved this dynamic programming question and we can move on to the next one. Similar questions. Best time to buy and sell stock for. Okay, so this is pretty much the same question. The only difference is that we're not limited by just 2 transactions here. We're actually getting input of k transactions. That's gonna be our limit. The solution is pretty much the same. First thing we want to do, we want to check if the lengths of prices, if it's empty, we return 0. Next thing we want to do, since it's a little bit different problem, we want to check if when k is big enough, if k is number of transactions is bigger than the half of our list of the array we're getting, of the prices we're getting, that means that we're not really limited by the transactions and that we can do as many transactions as we want. So just to save some time, we can literally add all the numbers up and just do it as we would do with unlimited transactions. So if k is bigger than equal to lengths of prices divided by 2, we would have some method self quick solve. We would pass prices to it and it's a really good habit to be able to define new methods and modularize your code. Your interviewer is going to really appreciate that. Def quick solve self prices. We define profit equals to 0 for I in range 1 lengths of prices if prices I is bigger than prices I minus 1. We added to profit. Profit plus equals, we add the difference to profit. Prices I minus prices I minus 1, and we return profit. And here we obviously return the result right away. Okay, we have this. Then we can go to our dynamic programming solution. We define 0 for I in range lengths of prices, for j in range k plus 1, just because we need to count for the for when transactions are 0. And here we're doing the same thing we did in our first solution for, let's say, t in range of k plus 1. We define max so far equals float negative infinity for I in range, here I'm going to start from 1 lengths of prices. We check max so far if it changes, max so far, and we check dp k minus 1 I minus 1 minus prices I minus 1, and dp k I, actually not k, it's t, and here it's t I. We max dp same number of transaction less days, and prices I plus max so far. And here we just return dp minus 1 minus 1. Let's check if we coded everything right. Looks okay here. Okay, we're successful here, and solution is successful. Is there any way to improve this solution? Actually, there is, and the logic is pretty much the same as for the previous one. We're not using the whole dynamic programming array, we're just using the 2 last layers. So instead of defining the whole array and keeping everything in memory, we can define even and odd. Even equals to 0 for I in prices, odd equals 0 for I in prices. And in here, if t divided by 2 equals to 1, we're doing current equals to odd, and previous equals to even, and else is current equals to even, and previous equals to odd. And what we're doing pretty much in here, we're just referring previous prices stays the same, referring current here and current here. Looks okay. And here we need to remember, we need to check what we're trying to return. So it's even -1 if k modulus k divided modulus k2 equals to 0. Else it's just going to be odd -1. Let's check if the logic is correct. And yes, it is correct, and we're improving our memory usage, and it's actually 100% better than for any other submission. So yes, that's it. That's the one of the really asked questions for dynamic programming. In my opinion, if you get how to solve this one, you'll become much better in dynamic programming in general, just because it's the most typical dynamic programming question you can be asked, and it really shows how you understand dynamic programming. And yeah, if you have any questions or any suggestions, please leave a comment down below. Obviously, let me know if you want me to solve any specific problems. Send the link to LeetCode problems, and I appreciate you watching my videos, and keep coding. Bye.